so here we go. We're going to talk about, we already covered this first part, so we're going to talk about, starting with the uncertainty principle, I guess, and then moving through. Now, the uncertainty principle is technically part of 6.4, but I didn't really cover that when I talked about 6.1 through 6.4, because we were spending so much of our time talking about PES, photoelectron spectroscopy. So I'll back up a little bit and talk about Heisenberg quickly. Just kind of a reminder on Heisenberg. Now, did you learn this last year? Heisenberg uncertainty principle? You guys didn't talk about this? Okay. I mean, this is a little bit more in detail than what I talked about with my classes either. Also, whatever word is supposed to go there. But here's the basic idea. So in order to figure out where something is, you have to see how it interacts with light, essentially, with electromagnetic radiation, or with sound or something like that. You know, we use sonar when you have a boat that sends a signal down and sees how long it takes to bounce back, and you can kind of map out the bottom of a lake or bottom of an ocean or something like that. It's the same sort of principle with electromagnetic radiation. We can tell where something is based on the light that it's giving off, right? So the reason that I can see everything in this room is because everything is giving off some sort of visible light, which allows me to be able to see it, okay? Now, what Heisenberg basically said is the problem with electrons and figuring out where they are is they are so small they're actually greatly affected by light. And so we talked about the photoelectric effect last time, and the idea that you shine electromagnetic radiation at a piece of metal and you can actually knock electrons off. You move the electrons because the light has enough energy. Electrons are so small that a photon can actually move an electron somewhere else, cause it to jump up an energy level or that sort of thing. So what Heisenberg said was, well, that's a problem because that means that we can never really know where these electrons and these atoms are, because if you hit the electron with electromagnetic radiation, which is the way that we would normally be able to see something, right, and then see how it interacts, it's already moved somewhere else now, okay? So you can kind of know where it was, but you can't know where it is because you moved it by trying to observe it. And the thing is, there are certain types of light that don't move electrons, right? Like infrared radiation doesn't move an electron, but the wavelength on infrared is so long compared to the size of an electron, it doesn't help you pinpoint its location at all, okay? You need something with a really short wavelength like X-ray or gamma ray or ultraviolet, but all of those have so much energy, they immediately move the electron somewhere else, okay? And so that's kind of the problem that Heisenberg said. He said we can kind of know its position or its momentum to some extent, but we can't know both at the same time, okay? We can't know both where it is and where it went with much degree of certainty. And so what that led to is the idea that we can't know where an electron is at any given time in the atom. It's not that we just don't have good enough technology yet. It's that fundamentally we can never, ever know. That's the Heisenberg uncertainty principle, okay? And so what that leads to is, well, we have to figure out some way to define where an electron is. And the analogy I gave my students last year was the best we can probably do is if I go outside of my classroom and there's something up on the window so that I can't see in, so it's blocking the window, and you guys are all in here, someone comes by and says, hey, where are your students? The best I can say is, oh, they're in the room. If they say, no, where exactly are they in the room? You know, where's this person in the room? Where's this person? Oh, I'm going to have no idea. I just know you're somewhere in the room, right? And that's kind of the way it is with electrons. And we call these rooms that the electrons could probably be in, we call them orbitals, okay? And so that's where you get the idea of orbitals from in quantum mechanics. Let's get through some of this stuff. You know what? I don't like doing it this way. I want to do it faster. We're going to completely skip quantum numbers. That is not on the AP exam anymore, which is a good thing because quantum numbers are stupid. I don't like them very much. I see their purpose. I get their use, but I mean, it's kind of weird. All right, so the rooms, the orbitals, like the s orbital, p, d, f. You remember talking about that last year? Okay, so that's ultimately what that comes from is Schrodinger made a wave equation. Now, his equation was originally meant to describe electrons themselves. He said electrons were waves. Heisenberg kind of disproved that idea. But then, ultimately, those people who were developing quantum mechanics said, hey, wait a second, we can use Schrodinger's equation here to help us define the region of space where the electron probably is going to be found. So they used his equation for something he hadn't intended it to be used for, but it worked. So if you solve Schrodinger's wave equations, you get these orbitals here, these S, P, D, and F different shaped orbitals, which are kind of like the rooms where the electrons can be found, okay? And again, this is a little bit more in-depth than we probably need to go with this. The p orbitals kind of look like dumbbell shapes. The s orbitals are spherical, as you saw. Let me just look at this. There we go. The d orbitals, they usually have 4 lobes, except for the one d orbital here that has the, it looks like a p, but then it's got a donut kind of around the middle of it. The f orbitals are a little too complicated for us to really worry about as far as their shape. So then what that leads you to, again, is this idea of orbital diagrams, okay? And all this is really showing is that there are electrons in this 1s orbital here. They will fill the 1s orbital first, then the 2s, 2p, and that just shows you the order that the electrons go into the different rooms, okay? Now, the analogy I gave to my students last year, not really an analogy, but the 2 things that I said that you need to remember about electrons, number 1, and most importantly, electrons are cheap, all right? And number 2, a little less important, they're antisocial, all right? So what that means is electrons, if this is an actual hotel here, this orbital diagram thing is a hotel, then that means an electron comes up, it's going to want to go into this 1s room first because it's the cheapest room. It's the room that takes the lowest amount of energy to be in, okay, if that kind of makes sense. So the first electron is going to go into this 1s orbital right here, and we usually show that by up arrows. Sorry, this alignment's off. The second electron that comes in, again, cheap, so it wants the cheapest room. Okay, now it doesn't like necessarily hanging out with another electron, but it will if it has to. All right, and it doesn't want to pay for this 2s room because that's too expensive. So it's going to go here. Now, to sort of compensate for the fact that it's in the same room as another electron, they will spin in opposite directions, and that's what this up and down arrow actually show. They're spinning in opposite directions, okay? And that helps them to be kind of in the same room at the same time, okay? The next electron that comes along, well, there's no space in the 1s orbital anymore, so now it's going to take a spot in the 2s orbital, and then it just keeps filling like that, okay? Once you get to 2p, here's where that idea of being antisocial kind of comes in, right? The first electron takes this 2p room right here. The second electron that comes in, well, there's another room that costs the exact same amount that's empty, right? So this electron is going to go here first. The next electron that comes in is going to go here, and then they come back and they start filling up the rooms. Okay? Does that make sense? Okay. So if you kind of remember that about the electrons, that's going to help you out as far as filling those orbital diagrams. That talks about the spin quantum number, which basically I just said opposite spins. So electron configurations are essentially a shorthand for the orbital diagrams. Okay, so you come back over here. Actually, let's look at the orbital diagram that I just drew. The shorthand electron configuration for the one that I drew here would be 1s2, 2s2, 2p6. Okay. Because we've got 2 electrons in the 1s orbital, we've got 2 electrons in the 2s orbital, and we've got 6 electrons in the 2p. Okay? So it's basically just a shorthand way of showing the same thing that the orbital diagrams show. All right? Anything else that I really need to talk about here? This does more about the orbital diagrams. This shows the same thing that I was just talking about. But if you remember that electrons are cheap and antisocial, then I think you can remember how these things fill. Okay, then we get into the periodic table, which I believe, well, no, this is all Unit 6 here. Is there anything else I want to talk about here? There are some anomalies to the electron configurations. They have specifically said this year in the, see, this is just a really long monster problem at the end. But they've specifically said this year that you don't necessarily have to remember the anomalies. You just need to know the typical ones. So, and I think we even talked about some of the anomalies, some of the unusual electron configurations in honors chem last year. I don't know if you guys didn't talk about it. Okay. It's not that big a deal, really, because we're not even talking about an AP Chem now. As long as you know how to do the basic electron configurations, you should be fine. And we'll do some practice on those in class. Okay? So, I mean, that's essentially it, I think, for 6.5 to 6.9. Let me make sure I didn't miss anything. The other thing that's in your reading guide that's not here is a little bit more about photoelectron spectroscopy, like number 19. But we will talk about that in class. All right. I'm trying to introduce you slowly to this idea of PES, first by telling you what it is, and then next by letting you look at some of the data and figure out what it's telling you. And then we're actually going to do some practice in a couple of days where we read some of the data from PES and see if we can figure out what it's telling us about the electron configurations of an atom. Okay? So that's pretty much it. Not a lot to it. It's basically a review this time around.
I remember all of it.
Okay, good. All right.